Welcome to this comprehensive lecture on neuroendocrine gland regulation. Today, we are going to explore the fascinating and highly complex communication system between your brain and your body's hormone factories. We will understand exactly how this delicate chemical balance keeps you alive, regulates your metabolism, and maintains perfect harmony within your body. To start, imagine you are driving a car on the highway and you want to maintain a steady speed. If you go too fast, you ease off the gas pedal. And if you go too slow, you press down harder. Your body does the exact same thing with its most powerful chemicals. The brain acts as the driver, constantly monitoring the levels of hormones circulating in your blood. This beautiful, automatic communication between your nervous system and your hormone-producing glands acts as the ultimate biological thermostat, ensuring you never have too much or too little. Now that we understand the thermostat analogy, let us look at the specific organs involved in this process. Formally, neuroendocrine regulation is how the nervous system controls the endocrine system. The main commander here is the hypothalamus, located deep within your brain. It contains specialized neurons that synthesize and release chemical messengers called neurohormones. These neurohormones are the crucial first step in a cascading command structure that regulates your entire body, acting as the initial spark that tells the rest of your glandular system exactly what to do and when to do it. Following these neurohormones, we find they travel through a highly specialized blood vessel network called the hypophyseal portal system. This unique network delivers them directly and rapidly to the pituitary gland, avoiding the general circulation. The pituitary then interprets these signals and releases stimulating hormones into the general bloodstream. These stimulating hormones travel far and wide to peripheral glands, like your thyroid or adrenal glands, prompting them to release their own specific hormones. It is a perfect, highly coordinated relay race of chemical signals that keeps your physiological systems running smoothly. This relay race we just traced is absolutely critical because it forms the foundation of human homeostasis, which is the vital maintenance of a stable internal environment. Without this precise regulation, our bodies would be completely unable to respond to stress, regulate metabolism, or manage growth. In real-world medicine, severe disorders like hypothyroidism or Cushing's disease stem directly from a breakdown in this exact pathway. By understanding this system, doctors can pinpoint failures and prescribe synthetic hormones to artificially restore life-saving balance, preventing the body from spiraling into chemical chaos. To truly master how these hormone levels are maintained, we must look at the mathematics of hormone kinetics. The amount of hormone in your blood depends on both production and destruction. We represent this delicate balance with a fundamental steady-state equation. H is the steady-state concentration of the hormone in the blood. R sub S is the rate of secretion by the endocrine gland. And K sub C is the metabolic clearance rate constant, which tells us how quickly the liver and kidneys remove the hormone. If secretion increases, the hormone level rises. But if clearance increases, the level drops. Before we move on, let us see this with a concrete example. Suppose a patient's adrenal glands secrete cortisol at a constant rate of 15 milligrams per day. Their liver and kidneys clear this cortisol at a rate of 1.5 liters per day. We want to find the steady-state concentration. We choose our fundamental kinetics formula because it perfectly relates secretion and clearance. By substituting 15 for the secretion rate and 1.5 for the clearance rate, we divide the daily input by the daily clearance volume. The final answer is 10 milligrams per liter, representing a stable, healthy physiological baseline. Now that we have used this formula, let us prove mathematically why organ health is so critical. Looking at our steady-state equation, what happens if the patient's liver begins to fail? The clearance rate, K sub C, would drop. Mathematically, as the denominator of our fraction decreases while the numerator stays constant, the overall value of the fraction must increase. This proves that without proper clearance, the hormone concentration H will dangerously spike, showing exactly why both production and clearance are vital for endocrine health. This brings us to an important question. How does the brain adjust that secretion rate in the first place? It uses a mechanism called negative feedback. We can model the pituitary gland's secretion rate using a linear negative feedback equation. R sub S is the current secretion rate of the stimulating hormone. R max is the maximum theoretical secretion if absolutely no feedback existed. H sub P is the concentration of the peripheral hormone circulating in the blood. And F is the feedback sensitivity constant, measuring how strongly the brain reacts. As the peripheral hormone increases, it sends a stronger inhibitory signal to the brain. Let us apply this negative feedback model to a real scenario. The pituitary gland secretes thyroid-stimulating hormone with a maximum rate of 20 units per day. The sensitivity constant is 0.8, and the patient's current thyroxine level is 15. We need to find the suppressed secretion rate. We plug these values into our equation. First, we multiply 0.8 by 15, which gives 12. This represents the brain physically reading the hormone levels and applying 12 units of inhibition. Subtracting this from 20 gives a final secretion rate of 8 units per day. So we have successfully calculated the suppressed rate. Let us look closely at the mathematical reasoning that makes this a biological break. In our equation, the term F times H sub P represents the inhibitory signal. As the peripheral hormone, H sub P, increases in the bloodstream, this multiplied term becomes larger. Because we are subtracting this growing term from a fixed maximum rate, the resulting pituitary secretion rate, R sub S, must decrease. This simple mathematical relationship elegantly proves how the body protects itself from chemical overload and hyperthyroidism. Now that we have proven the mathematics, let us visualize this entire system. On screen is the hypothalamic pituitary negative feedback loop. At the top, the hypothalamus sends a positive stimulating signal, shown by the green plus arrow, to the anterior pituitary. The pituitary then stimulates the target gland, which releases peripheral hormones. Notice the red arrows looping back upwards. These represent the peripheral hormones traveling back to both the pituitary and the hypothalamus, carrying a negative inhibitory signal, marked by the minus signs. This loop is exactly what keeps the hormone levels perfectly balanced. To wrap up our lecture, let us review the most important ideas. First, the hypothalamus and pituitary act as the master commanders, regulating your peripheral glands. Second, the actual amount of hormone in your blood is a delicate balance between how fast it is secreted and how fast it is cleared. Third, strict negative feedback loops act as biological brakes to maintain homeostasis. Finally, By translating these biological processes into mathematical models, we can understand and treat complex endocrine diseases. You now have a solid foundation in neuroendocrine regulation.